The next part of 4.6, trying to break this up into short videos, is how you deal with square roots that are in the denominator of a fraction. This technique is called rationalizing the denominator. Somewhere along the way, someone decided that in order to have a simplified square root answer, you are not allowed to have a square root in the bottom, which is kind of annoying because it generally is the same answer, but that is not considered simplified. The reason that I want to make sure that I teach this to you, even though it kind of feels a little bit silly, is when you take an ACT test or an SAT test or any type of standardized test, they will utilize this strategy. So I want to make sure you know how to do it so you're not stuck and not knowing how to get the final answer. So essentially what you're doing is you are looking at a way to make the bottom perfect. So you're looking at, first, can you simplify the fraction without worrying about square roots? Can you do any sort of reducing? Can you take any perfect squares? So start with kind of the basics. And then once you look at it and realize I still have a square root in the bottom, then you're going to figure out what do I have to do to get it to be perfect. So you kind of want to create a perfect square. So here, best way to explain it is to do it. We're going to go through 6 questions so you get to see different versions of this. So the first thing you want to do is see if 7 over 2 for this first one reduces, and it doesn't. Also check and see if either the 7 or the 2 is a perfect square, which it's not. So you want to tend to take those steps first. Then what you want to figure out is what can I multiply the bottom by? You're really focusing all your energy on the denominator to get it to be perfect. So to get 2 to be a perfect square, and if you think that perfect square list is still a good reference list, you needed to multiply it by 2 because then it will be a 4. So we're going to multiply the bottom by a 2 because then it's going to be 4, which is a perfect square. Whatever I do to the bottom, the denominator of a fraction, I also have to do to the numerator of the fraction. So now I have a square root of 14 on top and a square root of 4 on the bottom. I can't do anything with the square root of 14. It's not a perfect square. It doesn't have any perfect square factors. But now I can take the square root of 4, which is 2, and this is actually my simplified, or it's called rationalized answer. The reason I cannot simplify the 14 and the 2 any further is because the 14 is under a radical and the 2 is not. The next one, first thing you'll notice, 25 divided by 3 does not reduce. However, the one thing I can simplify it is the square root of 25. That is a perfect square. You get 5. That's the first thing I'm going to do, is since I noticed I do have a perfect square already there. Then I need to figure out what do I have to multiply 3 by to get it to be a perfect square. Well, if I multiply it by another square root of 3, it would be the square root of 9. Whatever I do on the bottom, I also have to do on the top. Now, on the top, the 5 is not in a square root and the 3 is, so I cannot multiply those together. I have to just leave them side by side. And in the bottom, I have a square root of 3 times the square root of 3, which is the square root of 9, which ends up being just 3. So this ends up being square root of 9, which is the square root of 3. Next one, 2 over 11 doesn't reduce. There's no perfect squares. I can multiply 11 by another 11. And keep in mind, it's still under a square root. Maybe I should write it like that so you get to see it better. Square root of 2 times the square root of 11 is the square root of 22. I am allowed to multiply them together because they're both under square roots. The square root of 11 times another square root of 11 is just 11 because you get the square root of 121, which is just 11. One thing that might be helpful to realize is if you take the square root of a number times the square root of that exact same number, you're going to get that number. The square roots will cancel out. So we kind of use that a lot for these. Few more. I want to show you a couple that do some extra simplifying. So the first thing on the first one, 80 over 10 reduces to 8. So if you notice that it's a fraction that reduces, reduce it first, and then oftentimes it makes it so much simpler to continue. And now I don't even have a denominator, so I don't have to mess around with that. 8 is not a perfect square. However, it does have a perfect square factor of 4, so we can break it down into 4 times 2. The square root of 4 is 2, so we get 2 root 2. The next one, 6 and 10 are not perfect squares. However, they do reduce to 3/5, or it may make it easier to see it as the square root of 3 over the square root of 5. The bottom is not a perfect square, but I can multiply it by another square root of 5 to get it to be a square root of 25. The top is the square root of 15. The bottom is the square root of 5 times another square root of 5, which is just 5. And that is a rationalized answer. And then finally, the next one, 64 is a perfect square. So you can actually break this down at the start into 8 over square root of 63. I can even go a step further and I can break the 63 down So I'm not really getting into the rationalizing yet. I'm going to break the 63 down into 9 times 7 because 9 is a perfect square. So I'm going to do a lot of extra simplifying at the beginning here. So I'm going to get it to look like this. 8 divided by 3 root 7. Now I'm going to multiply by the square root of 7 over the square root of 7. I get 8 square root of 7. On the bottom, I have a square root of 7 times the square root of 7, which is just 7. And then I have a 3 in front. 3 times 7 is 21. So there is my simplifying. So this is referred to as rationalizing the denominator, or in other words, simplifying fractions that have square roots in them.